Here we see an SN1 reaction where rearrangement has occurred, and the assessment asks us to show that mechanism. As always, we start these problems by numbering our carbons. Let's talk for a minute about how we did that. In the reactant, we just number them 1, 2, 3, 4, 5. We call the two methyl groups 6 and 7. We can't be wrong when we place our numbers there. Moving over to the product side, though, we have to make sure that the numbers match up. And you'll notice that 2, 3, and 4 are all CH2 groups. So we're going to make sure that that remains the same for 2, 3, and 4. Our methyl groups were 7 and 6. We've got two methyl groups. One will be 7, one will be 6. So we keep that consistent. Notice here that carbon 5 is a CH connected to a good leaving group. It's still a CH in the product, so we believe that this is probably carbon 5. That leaves only carbon 1, which is probably that one. By numbering these carbons, we see that the bromide is going to be leaving and some rearrangement is going to happen. Specifically, one of the methyl groups, 7 or 6, we've shown it as 6, is going to move away from carbon 1 and become attached to carbon 5. So if we wanted to make a formal list of bonds broken and bonds formed, that would certainly be on it. We're ready to start our mechanism, though. As an SN1 reaction given in the assessment, we know that bromine is going to start by leaving. And so that allows us to generate this carbocation. And we notice that in this carbocation, with the numbers still present, we can put the numbers back in. In this carbocation, we have a secondary carbocation next door to a carbon that is quaternary. Anytime you have a carbocation that is next to a more substituted carbon, rearrangement can occur. How does the problem tell us that rearrangement is going to occur? Because the C6 is no longer attached at carbon 1, so it must migrate. We can show the methyl shift in that way. When we show that methyl shift, that's going to generate a more stable carbocation, hopefully. If the rearrangement is going to occur, it will create a more stable carbocation. In fact, this is tertiary. Let's put our numbers back in just to make sure that we're still tracking that correctly. But we have, in fact, shifted from a less stable secondary carbocation to a more stable tertiary carbocation. Having made the more stable carbocation, we're now ready for the nucleophilic attack to happen. And so ethanol, using a pair of electrons on oxygen, can donate one of those electron pairs to the empty p orbital represented by the carbocation. When that happens, ethanol has brought along its proton, and so we've generated a molecule that has an acidic proton. With lots of ethanol in solution, that proton can be removed in an acid-base reaction to produce the product, completing our mechanism.